Isaac Newton did not discover that objects fall. Humanity had already noticed that, usually while dropping something expensive. What Newton explained was far stranger. The falling apple, the circling moon, and the moving planets all obeyed the same mathematical rules. So how did one difficult, secretive man turn gravity into a universal system? The short answer is that Newton could see order where others saw separate problems. The longer answer includes plague, prisms, private manuscripts, furious arguments, furnaces, counterfeiters, and possibly one perfectly ordinary apple. Newton was born at Woolsthorpe in Lincolnshire in 1642. His father died before he was born. When Isaac was 3, his mother remarried and moved away, leaving him with his grandmother for several years. It is tempting to turn this into a neat explanation for the adult Newton, who could be isolated, suspicious, and spectacularly unwilling to let an insult expire naturally. But people are not equations. We know the separation happened. We cannot calculate exactly what it did to him. As a boy, Newton built models, made mechanical devices, and filled notebooks. His family briefly tried to make him manage the farm. This was not a success. Newton was apparently more interested in books and machinery than in persuading sheep to participate in agriculture. In 1661, he entered Trinity College, Cambridge. The official curriculum still leaned heavily on ancient authorities, especially Aristotle. Newton quietly read newer thinkers such as Descartes, Kepler, Galileo, and Boyle. At the top of one notebook, he wrote a heading meaning certain philosophical questions, then began questioning nearly everything. This was Newton's basic habit. He did not merely learn an idea, he worried at it until it either broke or became mathematics. In 1665, plague closed Cambridge, and Newton returned to Woolsthorpe. The next 2 years are often called his miracle years, though that phrase can make the work sound suspiciously effortless. In reality, he covered pages with calculations, revised arguments, performed experiments, and kept much of it private. During this period, Newton established the foundations of his method of fluxions, an early form of calculus. Calculus is mathematics for quantities that change. It lets us describe an object's speed at a particular instant, or add countless tiny changes to find a total distance, area, or effect. For Newton, this was not decorative mathematics. Motion changes from moment to moment. If he wanted to explain falling bodies and curved orbits precisely, ordinary arithmetic was rather like trying to measure a river using bricks. If badly drawn lives and inconveniently complicated people are your sort of thing, subscribe before Newton withdraws the paper. Newton also investigated light. In a darkened room, he allowed a narrow beam of sunlight to pass through a prism. It spread into a band of colors. Many people thought the prism somehow colored the light. Newton argued that white light already contained rays of different colors, and the prism separated them because they bent by different amounts. This helped explain why ordinary lens telescopes produced colored fringes. Newton built a compact telescope using a curved mirror instead of relying on a large main lens. It worked well enough to impress the Royal Society, which elected him as a fellow in 1672. Then the trouble began. Robert Hooke, the Royal Society's brilliant and combative experimentalist, criticized parts of Newton's theory of light. Some objections were reasonable scientific debate. Newton treated criticism less like assistance and more like someone entering his house carrying a small torch and several cans of oil. He wrote lengthy defenses, quarreled over credit, and withdrew from public discussion. This pattern would repeat. Newton wanted recognition, but publication brought critics, and critics brought emotions he managed with all the delicacy of a falling anvil. Then there is the apple. The familiar version has an apple strike Newton on the head, instantly delivering the law of gravity. There is no good evidence for the head impact, and the theory was not created in one afternoon. But the entire story should not simply be discarded. Several early accounts connected to Newton himself. William Stukeley later described a conversation in 1726 in which the elderly Newton recalled seeing an apple fall and wondering why it moved toward the earth. That story was written down decades after the supposed event. It may preserve a real memory, a polished anecdote, or some mixture of both. The careful version is that a falling apple may have helped focus Newton's thinking. It did not hand him several hundred pages of mathematical physics while the tree waited politely. The important question was not simply why the apple fell. Newton wondered whether Earth's pull might extend far beyond the orchard. Could the force acting on the apple also reach the moon? Imagine throwing a stone horizontally. It travels forward while falling, then hits the ground. Throw it faster, and it lands farther away. In Newton's famous thought experiment, an impossibly powerful cannon fires from a very high mountain. If the cannonball moves fast enough, the curved Earth falls away beneath it at the same rate that the ball falls toward Earth. The ball keeps missing the ground. It is now in orbit. That is the central intuition. The moon is falling toward Earth, but it also has sideways motion, so it continuously misses. An orbit is falling with excellent timing. Newton's laws of motion described how objects respond to forces. An object continues in uniform motion unless a force changes that motion. A stronger force produces a greater change, while a more massive object resists change more strongly. Forces between two bodies act mutually, not in only one direction. His law of universal gravitation then made the enormous claim that every body attracts every other body. The attraction increases with their masses and weakens with the square of the distance between them. Move twice as far away, and the force becomes 1/4 as strong. This joined heaven and earth. The planets were not guided by one set of celestial rules, while apples used a cheaper local arrangement. The same mathematical framework could explain falling bodies, planetary paths, the moon's motion, comets, and aspects of the tides. Newton did not achieve this alone, and he did not finish it during the plague years. Kepler had described planetary motion. Galileo had transformed the study of falling bodies. Hooke, Christopher Wren, and Edmond Halley had discussed an attraction that weakened according to an inverse square rule. The missing piece was a rigorous mathematical demonstration connecting such a force to planetary orbits. In 1684, Halley visited Newton and asked what path a planet would follow under an inverse square force. Newton answered that it would be an ellipse and said he had proved it. He could not immediately find the proof, which is a strong move when the visitor has traveled from London specifically to see it. Newton recreated the argument and kept expanding it. Halley encouraged him, managed tensions, and shepherded the work into print. The result was the Principia, published in 1687. The Principia did not just offer a gravity formula. It presented a mathematical system of motion and showed how evidence from Earth and the sky fitted together. It became one of the foundational works of classical physics. Newton could describe gravity's effects with extraordinary accuracy, but he did not provide a physical mechanism for how attraction crossed empty space. He preferred not to invent an unsupported explanation. Centuries later, Einstein would describe gravity differently, as the curvature of spacetime. Newton's theory became an approximation, but an exceptionally useful one that still works for a vast range of ordinary problems. Meanwhile, Newton's reluctance to publish his calculus created another disaster. The German mathematician Gottfried Wilhelm Leibniz developed calculus independently and published his version first, using notation that proved clearer and eventually became standard. Newton had worked on his method earlier, but circulated it privately. A priority dispute grew into an international mathematical feud. Both camps accused the other of borrowing. Newton, by then president of the Royal Society, oversaw an inquiry that ruled in his favor. He was not exactly a detached observer watching from a nearby hedge. The fairest conclusion is that Newton and Leibniz developed calculus independently. Newton reached key ideas earlier in private. Leibniz published earlier and gave mathematics much of the notation it still uses. The dispute damaged reputations and divided mathematical communities, largely because two geniuses found sharing credit more difficult than inventing calculus. Newton also spent years studying alchemy. He read coded texts, copied recipes, built furnaces, and experimented with metals and chemicals. This was not simply modern chemistry, but neither was it merely foolish magic. In Newton's time, the boundaries between chemistry, metallurgy, medicine, and alchemy were unsettled. He searched for hidden processes that might explain how matter transformed. The same mind that looked for universal order in planetary motion also looked for secret active principles inside a furnace. His alchemical work remained largely unpublished, leaving later admirers to discover that the great symbol of rational science owned rather a lot of mysterious recipes. In 1696, Newton left Cambridge to become warden of the Royal Mint in London. The job could have been comfortable. Newton made it extremely active. England was carrying out a major recoinage, while clippers shaved silver from coins, and counterfeiters manufactured false money. Newton studied records, interviewed informers and suspects, followed evidence, and helped prosecute offenders. The man who had tracked the moon now tracked people making suspicious shillings in back rooms. He became master of the mint in 1699 and remained there until his death. His concern with measurement and exactness transferred neatly from planets to coin weights. People, unfortunately, were less predictable. By his later years, Newton was famous, wealthy, knighted, and president of the Royal Society. He died in 1727 and was buried in Westminster Abbey. The clean legend is Newton beneath a tree, receiving gravity in a single flash. The real achievement was harder and more interesting. He took observations, old discoveries, new mathematics, criticism, experiments, and years of private labor, then forced them into one system. Newton showed that the universe could be understood through common laws. Yet the man who unified earth and heaven struggled constantly with the smaller forces between human beings. The apple fell quietly. Newton supplied the argument, the equations, and several decades of unnecessary conflict.